All right, the next section here, 1.4, is how chemical bonding theory actually developed. So if you think back 150 years ago, two fellows, August ch1lg from Germany and Archibald Cooper from Scotland, they independently showed that carbon is tetravalent. So tetravalent, what does that mean? Tetra means four. Valent means it's valence. So carbon has those four valence electrons, and it makes four bonds. Okay? Four valence electrons, just like we said before. Four valence electrons makes four covalent bonds. And they showed that by pretty clever means of their time in determining how it is that how many hydrogens can be joining with carbons and so on, by careful measurements of masses and determining of molecular formulas and so on. So ch1lg went beyond that to suggest that carbon can form chains and can form rings. He actually had a major epiphany when benzene was a very commonly known substance of the time, and he could never figure out how it was that there was that certain number of hydrogens with that certain number of carbons until he finally figured out that carbon can form a ring. So benzene is a six-membered ring and actually has some double bonds in it, which we'll talk about later. But that realization is what really got the field of organic chemistry going. So a little later in the 1800s, a couple of people, Van 't Hoff, Joseph Lavelle, showed that carbon is tetrahedral. You should recognize Van 't Hoff from a couple of places in general chemistry. He did work with colligative properties of ionic solutions, so that lowercase I that you used to define how many ions something breaks up into, for instance, came from him. So here's what a tetrahedron is. Tetrahedron is a four-sided, four-pointed polygon, right? So, it's a three-dimensional shape that has four sides. So if you line up four triangles and you make a pyramid out of them, that's a tetrahedron. So it has a triangle for a base, and then three triangles come and form a point that way. So another way of thinking of a tetrahedron is like a tripod. So three legs going down and one going straight up. Okay? That's if you have something in the center of the tetrahedron and you're pointing out towards the points of it. So the structure of methane, that's methane CH4, is actually tetrahedral. And this is how we draw a tetrahedron on a flat piece of paper. We have two of those lines that are within the plane of the paper. Okay? The bonds in the plane of the page are just drawn as straight, normal lines. You have one of them that's coming forward towards you out of the plane. So that's the wedge line. So imagine that the up one and the lower right one are within the paper. This wedge one is coming out of the paper right towards you, and right towards your face. The dashed line one is the bond that's receding into the page. So it's going backwards behind the page. So a tetrahedron can always be defined by having two of those bonds that are flat within the plane of the paper, one towards you, right? Let's write that, towards, one going back, away from you. So become familiar with that. It will be very common for us to have the wedge line and the dash line to be next to each other in a tetrahedron. That actually looks like a tetrahedron, where having something like this, where I have a wedge line going one way and the dash line going opposite, that does not look like a tetrahedron. Okay. That's just right, not a good. Okay, so make sure and you'll always be fine. It doesn't matter what direction these things are, but you'll always be fine as long as you draw the wedge line and the dash line next to each other. That will always make for a good tetrahedron. For instance, if I draw a shape where we go up and down, okay, with two straight lines, I make sort of an upside down V with those up and down lines. Then I can draw going up a wedge line, and then also going up, but a little to the side of it, a dash line. Okay? that's a perfectly valid tetrahedron because, again, I have the wedge line and the dash line next to each other, sort of on the top side of this tetrahedron, and then both going, one going down left and one going down right, are the two bonds that are within the plane of the paper. Okay, so that's a perfectly fine tetrahedron as well. But it'll actually be very common for us to draw the two in the plane, one of them going up, one of them going down to one direction, and then the wedge and the dash going down off to the other direction. That's going to be the most common tetrahedral way that we'll draw things. So let's start talking about why it is that bonds form, and we'll get into a little more of this in a bit. But it turns out that atoms bonded together in a stable compound, it's a favorable energetic change that's happened. Okay? They have lower energy than individual atoms. If I had in CH4, comparing the CH4 with individual atoms with 1 carbon and 4 hydrogens, it'll be much lower energy with those atoms that have combined together. So it turns out that energy is always what? Energy is always released when a bond forms. It's always going to be a favorable reaction like that, as energy will always be given off in order to form a bond. It comes from attractions of those electrons to the positive nuclei in each atom. So that's going to be a favorable interaction. Those electrons within the bond will actually be attracted to those nuclei from each of those atoms. Okay? So there are actually two kinds of bonds. There are ionic bonds. In ionic bonds, we transfer electrons first, then the ions attract. So in a salt like sodium chloride, it starts out where sodium gives away one of its electrons to chlorine. So we get an Na plus that is attracted very strongly to a Cl minus. So we've transferred the electrons to set up those oppositely charged particles that are pulled towards each other. Okay? In a covalent bond, electrons are shared. So where I have a hydrogen with its 1 electron, will share that 1 electron with another hydrogen, so that each of those hydrogens now has access to 2 shared electrons. Okay? So let's talk a little bit more about how we can draw structures of these types of things and to indicate their bonding patterns and so on. So it turns out a Lewis electron dot structure will show valence electrons as dots that can be shared between atoms. Okay? And covalent bonds. We can draw Lewis structures of ionic compounds too, but we're not as concerned about those in organic chemistry anymore. So a Lewis electron dot structure, I can do those of just individual atoms showing their valence electrons. Okay? The inner electrons, the ones in the inner shells, those inner shells are full, so those don't participate in any of the bonding. It's only in those outer shells. And those valence electrons, you can always tell that just by the group number. Like we said earlier, the number that's up on top of the periodic table. So hydrogen with its 1 valence electron, just like we showed before, will share it with another hydrogen, and so on. So those are going to be useful for us to a certain extent, right at the beginning, as we're just really just trying to understand where those electrons are within the molecule. But it will be pretty inconvenient for us once molecules get any bigger than these small things to be drawing all of those dots everywhere all throughout the thing. So our first little time saver are called line bond structures. They're sometimes called ch1lg structures, named after the original progenitor of carbon's main bonding patterns. So Lewis was the first one that figured out that electrons can be shared. ch1lg was pretty specific to carbon. So in a ch1lg structure, pretty much the same as those Lewis structures, except we'll represent a shared pair of electrons as a line. So these will be very common for us. When I draw 2 hydrogens covalently bonding, I'll just draw a single line between them to show that shared pair of electrons. So take a look. Here's 3 very common small molecules that we'll be dealing with a whole bunch. CH4, NH3, H2O. So the Lewis structure of CH4 comes from carbon, which had its 4 original valence electrons, and then each of those 4 valence electrons will pair with a hydrogen. Right. And you can either draw those 2 electrons side by side in those bonds, or you can draw them sort of stacked. Here, just draw it again here with, I can draw here, those 2 kind of next to each other, right on the kind of sideways in the bond. So as long as you indicate that there are 2 electrons that are 2 dots that are between 2 atoms, we're just going to assume that those are shared between the atoms. So that's where carbon made 4 bonds. Carbon has satisfied the octet rule, where these atoms in the main group generally tend to have 8 electrons around them. So nitrogen, 5 valence electrons. I'm going to go 1, 2, 3, and then I'll put 2 of them together. We'll see why that is in a second. So in order to get up to 8 with nitrogen, we form 3 covalent bonds. So that's why NH3 is a compound. 3 of them get paired with nitrogen, and then we have 2 remaining that just are on nitrogen and are unshared. So those are called lone pairs. Lone pairs are unshared electrons. So they'll always exist as a pair of electrons that came originally from that atom, and they're not shared with the other atom. So one more time here, water, we'll start with 6. All right, 1, 2, 3, 4, 5, 6. So if I do it that way, I end up with 2 pairs and then 2 that are unpaired. That's why oxygen will make 2 bonds, and we'll be left with 2 lone pairs. Drawing ch1lg structures of these, really pretty simple. As long as we start to recognize that carbon's making 4 bonds, I can just draw CH4 as carbon with 4 lines going out to those hydrogens. Okay? Nitrogen, NH3, right? And then I'm going to draw those lone pairs still as dots. So in those ch1lg structures, we draw lines for bonds, but dots are lone pairs that are originally on the atoms. Okay? So H2O, 2 bonds, and 2 lone pairs. Right? So let's just take some of these patterns that we talked about in order to get us to see how these elements tend to bond with each other. The normal number of covalent bonds depends on the number of additional electrons required to reach the noble gas configuration. So hydrogen has 1 of its own valence electrons. Okay? It's just in 1s1. Helium, the next noble gas along the line there, has 2 valence electrons. So that's why hydrogen just forms 1 covalent bond. If we look up in all these structures, hydrogen brought 1 of its bonds in, while the other atom it's bonded to brought the other electron in to make that bond. Okay? So hydrogen will always make just 1 bond. Hydrogen will never have any lone pairs on it because there's no room for them. All hydrogen has is that first shell that can only hold 2 electrons. So if it has 1 of its own and it gets 1 from another element, then that's about it. So carbon has 4 valence electrons, nitrogen 5, oxygen 6. All these halogens have 7, right? So again, let's use the octet rule for carbon, nitrogen, oxygen, and at least for fluorine. Okay. The octet rule will be violated a bit sometimes in some of our other structures, but the octet rule will almost always, we can at least assume for now that the octet rule will apply to C, N, O, and F. Okay? So those 4 in the second row. So carbon then, in order to get up to 8, it makes 4 bonds, nitrogen makes 3, oxygen makes 2, and the halogens generally make 1. Fluorine will always make 1 bond, chlorine, bromine, and iodine can actually make more. So this is just a starting point. Those non-bonding electrons are the valence electrons that are not shared. I'm going to typically call them lone pairs. So get used to that kind of terminology, but your book may at times call them non-bonding electrons. Right? So be familiar with these general bonding structures, with carbon making 4, with nitrogen making 3. And think about this. If nitrogen makes 3, it has to have a lone pair on it in order for it to have an octet. Right? If we have 3 covalent bonds, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen, 2 bonds and 2 lone pairs. Halogens like fluorine, 1 bond and 3 lone pairs. Notice in all of these cases, there are 8 electrons around those atoms. Remember, each of these lines is 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So take a really good look at these structures here. If I were you, I would draw out these sort of structures, right, along with H, just with its 1 bond. H, C, N, O, and F. I would draw out those structures at least a couple of times on your piece of paper. Right? And maybe have those in a place where you can refer to them, because we're going to need to get used to the fact that nitrogen will be making 3 bonds with 1 lone pair, that oxygen will be making 2 bonds with 2 lone pairs, okay? That fluorine will just make 1 bond and it'll have 3 lone pairs, and so on. So put those on a little flashcard or something like that, just somewhere where you can refer to them. But I wouldn't just try to memorize that by rote. I would understand, sort of where it comes from. How many bonds we needed to make an octet, and then how many lone pairs will be left over, not bonded. Ready?